Hello everyone, welcome to this video. In this video we shall see question from June 2015 consisting of 4.75 marks. So for this question we need to determine which of the following polynomials out of these four polynomials, which one are irreducible over the indicated rings. So we need to tell this over reals, this over rationals, this over integers and this over finite field, right? So let us get started. So the first polynomial is of degree 5. So what test we can apply onto this? Oh, and we need to check it for over R, right? So you might be thinking we do not have any test to check whether the polynomial is irreducible or reducible over R. So well, you know, there is a fundamental theorem of algebra which says that every polynomial with complex coefficients has exactly n roots. But if we have coefficients in real, we can say that it has at most n roots, right? So moreover, if the roots are complex in nature, they occur in pair. Say if a plus iota b, this is a root, then a minus iota b must also be a root. So whenever there is a complex root, its conjugate is also the root. Therefore, the complex roots, they are always even in number. So now you see the degree of this polynomial is 5. That means we should have at least one real root for this polynomial, right? So this you know by the results. Therefore, if you have one real root, say a, then x minus a would be a factor of the given polynomial. You do not have to calculate what is a over here because that is not the thing that we are looking for. We are only looking whether the polynomial is reducible. This polynomial is reducible or irreducible. So now you have x minus a as a factor. Therefore, the polynomial should be reducible in nature, right? So now this polynomial is reducible. Therefore, this option A is incorrect, right? So this option is incorrect because they are asking for irreducible polynomial, right? So let us move on to the second one. This polynomial, this is of degree 3 and they are asking whether they are this is irreducible over Q or not. So now we can apply mod p irreducibility test onto this polynomial. You may go for any other also, right? So what does this test say? It says that if p is any prime number, then we reduce this polynomial onto some other polynomial f of x, in which the coefficients of this polynomial, whatever the coefficients are, they are reduced modulo p, right? And if the reduced polynomial fx bar, this is irreducible over z px, that is p module, right, integers modulo p, then the original polynomial fx is irreducible over q. So this is the test. So let us see, and we need to find this p. If we find any p such that this thing happens, then our original polynomial is irreducible over q. So in this case, p is 3. If we take p is 3, we have to check this by our own, what p should we take, right? So our polynomial, this f of x, which was having coefficient 1x cube plus 2x square plus 1x plus 1, right? This polynomial, say this is f of x, this is reduced to this polynomial. Now, when you divide 1 by 3, you will get the remainder as 1. So this remains unchanged. When you divide 2 by 3, you will get the remainder as 2. This remains unchanged. When you divide 1 by 3, again the remainder you will get as 1. So this is also unchanged. When you divide 1 by 3, again the remainder is 1. Therefore, this polynomial is same as this polynomial when we take p to be 3. So there is no change, no problem in that. But now we need to check the irreducibility of this polynomial over Z3. and the elements of Z3 are 0, 1 and 2. Therefore, let's check it one by one. So, in Z3, what we can do, we can look for its root. So, we can check for f of 0. So, now f of 0 comes out to be 1, which is not equal to 0 mod 3. Therefore, this is not a root. Again, for 1, this is not a root. For 2, this is also not a root. I hope you can do this, right? So this comes out to be 5, and in mod 3 you just have to divide 5 by 3 and the remainder is 2. Therefore this is also not equal to 0 mod 3, right? Therefore the given, as there is no root for this polynomial f(x bar) in Z3, right? Therefore by the above test, this is irreducible over Z3, and by the above test, the original polynomial fx, that is also irreducible over rationals, right? So this option is correct. So option B is the correct option. So this is the correct option. Let us move on to option number C. So option C, we have, in option C we have a polynomial with degree 3, right? One second. Yes, we have a polynomial of degree 3 over z, right? So we can apply Eisenstein's criteria over here. All the coefficients are are integers, right? So we can find any prime number p such that all these conditions are satisfied. So by hit and trial method, you will see p is equal to 3 satisfies all these. P is equal to 3 does not divide p square, that is 9, does not divide the constant term, right? Then p, which is 3, divides this term. P divides -6, this term. P divides this term 3, right? And p does not divide 1. So all the conditions are satisfied. Therefore the given polynomial is irreducible over Q. Now they are asking over Z. We have a result that irreducibility over Q implies irreducibility over Z. This result was given by Gauss. So this thing is also true, right? So the given polynomial is irreducible over Z. So this option is also correct. Let's move on to our last option, which is the polynomial of degree 4, and we need to check it over this field, right? So this field has only two elements, 0 and 1. So we may check for its root. If we found a root, we say that this is reducible, otherwise we'll have to look for another methods, right? So f of 0 would be, it comes out to be 1, which is not 0 mod 2, and again f of 1 comes out to be 3, which is equivalent to 1 mod 2, which is also not equal to 0 mod 2. Therefore we do not have any root over here, so we cannot conclude anything from here, right? Because the degree of our polynomial here is 4, and the result is valid only for polynomials with degree 2 and 3. Remember that, right? So we cannot conclude the polynomial is irreducible from here. So we have to check for its factor manually in Z2, right? So what could be the factors of polynomial with degree 4? It could be either of degree 1, it could either be of degree 2. Of degree 3, they'll automatically be obtained when you check for degree 1, right? So for degree 1, what are the possible values? So now we are looking for degree 1. That means this thing x, the coefficient of x should be non-zero. So this cannot be the case. The only possibility is you have 1 over here and 0 over here, right? Another factor that we could take is 1x plus 1. So these are only the factor 1 degree factors of this polynomial, which may be a factors, right? These are the only possible terms. So we'll check for one by one. So you clearly saw that by long division of the given polynomial, this was the given polynomial. When you divide this by x, you will get the remainder as 1, which is not equal to 0 mod 2. Therefore this is also not a factor. And you may similarly check for this one. This is also not a factor. So again we'll move on to degree 2. For degree 2, we should have this coefficient of x square as non-zero. That means it should be 1, right? Because we are looking for coefficients in Z2, Therefore, the coefficient could only be 0 and 1, right? So this has to be 1. This is fixed. Now you can change the coefficient of x and the constant terms. The coefficient of x, firstly I'll take it to be 1 1, then 1 0, then 0 1. One case is that we can take it both to be 0 0. So in that case we'll have 1 into x square plus 0x plus 0, right? So again, x square, this is not a factor because we saw x is not a factor. Again, this thing could be written as x into x plus 1. This is again not a factor because x is not a factor. We already checked for this. So we are left only to check for these two. So we can check them one by one. So let's look one by one. So let us look for this factor. When you divide this polynomial with this polynomial, you'll get the remainder as 0, right? So we got a factor for this polynomial. Therefore, we do not have to look for another factor. This is not required as of now because you have limited time in questions. Therefore, now we have a factor for this polynomial. Therefore, this polynomial is reducible over Z2, right? Therefore, this is also not a correct option. So the only correct options are, let us have a look. This is only B and C. This is the incorrect option. This was the correct option, right? So the correct options are B and C. Well, that is it for this video. Thank you for watching.